All right. So now we come to the HPC application in HPSF WarpX. Exactly, we, like Emrex, we try to join really as inaugurated members, and we nearly made it. So what I will talk about today is where, in our view, do HPC simulations go? And the simulation I talk about is called WarpX. WarpX is an application that's now close to 10 years old. Oh yeah, should be 10 years today, actually, this year. And what we do is we model fast charged particles for a lot of applications, and I'll show you in the slide what this means. What I will talk about today are the following aspects. A, who are we? What are we doing? Then B, what are HPC simulations still doing in the age of AI, right? What's our place here? And I'll show you a couple of examples. I will not talk about LLMs today, because everyone can talk about LLMs. I'll talk about machine learning that we found already useful, and LLMs we can talk in breaks. And then the last section, I will ramble a little bit about community challenges and things we would like to advance over the next year, and we think that are great topics for HPSF, and where we're really interested in your thoughts and ideas. So who are we and what are we doing? What I'm showing here is also naturally a really work of a lot of people. Specifically, WarpX is developed by more than 120 active contributors, and users are multiple of that. The contributions started in national labs, contributed from universities, likewise international research partners, and now actually multiple fusion startups as well that contribute back and not only use the code, which is a really nice way to interplay. What is WarpX? WarpX is so-called particle cell code. It's a particle mesh method that does electromagnetic and electrostatic and magnetostatic solutions. What we do is we discretize our whole problems on particles and fields. That's a way to separate short and long-term interactions in a very efficient way, specifically if you have relativistic and retarded effects in physics going on. That means you have an effect that takes some time because it's limited by speed of time to reach somewhere. These are the potentials that we solve. The applications are in laser plasma physics, particle accelerators, extreme light sources, fusion devices, plasmas, astrophysics, really wide because it solves really fundamental Maxwell's equations with all the physics involved. We have essentially, this is our core physics, but then we have built a multi-physics model and code around this. So we solve like quantum problems around this, fusion processes, nuclear physics, collisional physics, and all of these. And really what makes it an HPC code is it's rooted in portable multi-level parallelism from CPUs to GPUs. Then we use Emrex essentially for really making sure that we can use a whole HPC cluster, load balancing, all these features. And then we make this whole thing useful and scalable and hopefully interoperable as much as possible by using open APIs, schemas, doing in situ processing, and having really an open community ecosystem. And WarpX itself was recognized in 2022 with the Golden Bell Prize. The applications, I'll give you a few visualizations. So we came originally really from particle accelerator research. We tried to build more compact accelerators by using powerful lasers and shooting them at plasmas. That's very similar to large accelerators that you know around the world, from SLAC to LHC, which are miles long. What we try is to shrink them, but we can also model those actually, and specifically the parts where really action is happening in them, where particle beams collide with particle beams. These are things that WarpX can model in really great detail. Related to shooting lasers at stuff, there's actually a way to accelerate also heavy particles, and that is very closely related to the physics that, for example, is researched in Livermore at the NIF, where we can research, for example, interaction of powerful lasers with the surface of capsules, and research how heavy particles start, compress, and heat targets. And then related to this, there are now many in the last years startups in the space of fusion that try alternative concepts to the big ones. So the big ones are tokamak fusion with magnetic fields and the one I just mentioned, which try to build complex devices using magnetic mirrors, like all funny applications really of electromagnetism to build like new great applications. And then related as well, astrophysics. Like, for example, our colleagues in the Emrex team, they also research, for example, pulsars with the same code. How can you model those? Or microelectronic devices, because you can extend really on this toolbox and build more and more. Now, the best way to understand WarpX is naturally just to look at the spec graph. It's very clearly from this graph, if you just look in the corner over there, no, that's a joke. The application actually is built like this. So we root naturally on the performance portable stack, CUDA, OpenMP, SYCL, HIP, and MPI. Our root really that we build on is a strong dependency is Emrex. There are our containers. That means something like a field on 10,000 GPUs, allocate, boom, there it is. Communication between those. Solvers, like Poisson equation was just mentioned, portability and utilities. Then a very big I/O stack, building on things like HDF5, Ardios, schemas, and so on. And then math libraries where we can use them in solvers. And then on top of that, really already our domain science level starts. So that's where we implement like physics modules, where we start to embed machine learning models, where we build Python bindings to all of these things to make things modular. And then WarpX is our flagship code, but because particle and cell as a method is very portable, we also have more specialized codes. So for example, WarpX we can use to build a source, a very new compact accelerator, but if you want to build a whole system of a compact accelerator, we have, for example, the ImpactX code that goes for the long scale, while WarpX does the short scale. And then we have more specialized ones than, for example, for plasma wave fields, and I mentioned microelectronics. And all of this, again, is then wrapped into Python interfaces, into standard interfaces. And so in this very simplified schema, this is how we try to separate work and how to contribute to each other's software stacks. The whole thing, as you saw before, is embedded in a lot of documentation and CI. We're currently about to adopt the same GPU runtime CI from ALEC and SEC that Emrix already adopted, and this is really a big help for us to get our physics integration tests to continue to actually run on all these platforms that we developed it for. And then I will talk about at the end of the talk is also about deployment and the challenges that we face. And when you think about like what are our user bases, how can we actually ship to all of them and build things like containers, for example. Quick overview of our user base. We were originally rooted in the US, have a lot of users in universities, national labs there, and in startups. But naturally, there's a big landscape as well for really science facilities, and this is like one dot is a science facility around the world that uses WarpX for these different applications that I've shown you. Steadily, from tracking our users, we think there are like roughly 200 users every day building new WarpX input sets by tracking them, going back to documentation and reading how do I write a WarpX input set, what was option so-and-so. That would be a bit more tricky to track in the future because they now just asked Claude to go there. So let's see how unified we can still measure how users actually access our documentation. All right, that's us. Now the question is, what's still our purpose here, right? Why do we still need HPC simulations in the age of AI? And I want to give you 3 examples how we think that HPC simulations are pretty fundamental and how we can really do great new science cases by connecting them to machine learning surrogates to build so-called digital twins. And then one thing that we think is really missing in HPC generally is how we can introduce differentiable modeling in simulations and why we need this at all. So let's go into these 3 topics. One very classic thing where machine learning has us a lot is to train fast surrogate models. So surrogate models just means replacement model. And what you want to do is you want to create really high quality data, in our case from a WarpX simulation, for a piece in our case, particle simulation, particle beamline from left to right, you see these gray, blue elements. But the gray elements are super expensive to model, and everything else that you want to do in between is just super cheap. So you essentially would do something like spawn up 1,000 GPUs, do a big simulation, then run a 1 GPU in between, do 10 or 100 elements, and then go back to this huge HPC simulation back and forth. And specifically if you want to optimize a problem, like building like a new accelerator, this is quite costly, right? It's very sequential, you have to spawn it up and go back and forth. And so what you can do is you can really rely on HPC simulations, and what we did is take WarpX simulations and train them. In this case, we took 256 GPUs, ran them for 4 or 5 hours, small system example, trained the model, and then instead of optimizing on this pre-trained system, we used only the fast simulation part and the pre-trained surrogate from WarpX and did a full optimization loop over this combination. So we embedded in a small HPC simulation that only uses a few GPUs, in this case 1 GPU and a surrogate model, did thousands of optimizations on them, and then we got a new result and said like, oh, by the way, if you tune the parameters, the blue parts here, like this and this and this in your simulation, then you should get a way better beam out of this. So that's great, but now you're in surrogate world, and if everything is true there or not, it's not really true, or not really sure. So what you take at the end is you take your final result after thousands of optimizations and put everything back into the really expensive HPC simulation because you want to validate, right? You want to validate all of your assumptions or your effective models. And so we did this, and then we did basically one big simulation at the beginning, trained thousands of small simulations, and then one big simulation again at the end. And we could validate that actually the solution that we found in surrogate space was actually valid also in real space. So this is really cool as an application, right? It's whenever you think about like having to bridge scales, like in accelerators or in fusion science, this is a way how you can embed very specific knowledge from very good HPC data and be able to get like really orders of magnitude dramatic speed up in the overall workflow that you're interested in, not your individual simulation. All right. Then we document this, and that's, I think, is really core for us. Is like it's not only that the user can just take this and now build a new physics problem from it, but you can also with that really interact with computer scientists, saying like, well, by the way, your surrogate model is really basic. You could do this way better, and this is the way to do it. You just adopt this, right? Yeah. So you have really the connection really from different domains that have to talk to each other, and can start from there. Second part, digital twins. I'll put the definition of that up in a second, but I'll show you what we do now. HPC simulations are now, for us, often just a part of a really bigger interplay. We have experimental facilities where people really do measurements, right? They shoot lasers, they run applications, and so they sit in a control room that looks a little bit like a spaceship, right? You have tons of screens. It's actually, I mean, it's for a modeler, it's a dream. We have 2 little screens for that, but they have screens everywhere. Tons of knobs, and they can control their machines. And part accelerator is roughly 100,000 knobs to turn on. And they visualize and they try to optimize, like get the beam lifetime up, get as much charge in there as possible. And what we did is we built another component for this one where we can visualize models, and I'll show you how this goes in details. We connect what we can model with the measurement database that I already built, and we build from that ML models. I'll show you the purpose in a second. What we do then is simulations run notoriously slow. And so what you can do is you can continuously measure data, but sometimes if you want to build a new model, what you do is like, well, I would like to have a few more simulations for the data that's in there. And so what we can do with this workflow is something like, let's measure today a long campaign, and overnight we run just 100 HPC simulations and try to get more data points to what we want to do tomorrow. And that way you can actually plan a campaign. They usually go like 2 to 4 weeks at a time to say like from one day to another, you can explore more and more regimes from that. And so the connect is basically the HPC space, getting these slow but very precise updates, and then doing model building with new streaming data that comes in from the experiment as it goes. And with that, we have basically built up these databases and these interfaces. And here's an example of how this could work. So let's say you measure a couple of data. So we had a position of a laser spot, and we measure just, okay, this is the number of protons that we generate. Protons are important. We use them for radiating tumor cells. We use them to like investigate fusion processes. But we don't have a good model like analytically can we write down. It's like, where can I maximize the number of protons that I need for this experiment? So we do experiments, we do simulations, and they absolutely don't match. And that's quite common because experiments are noisy. There are lots of knobs that you don't know. So you could model them, but you can't put them in your simulation because there are too many knobs to see how exactly is the thing aligned. So what we do is we build 2 models. We build them A from the experiment, B from the simulation, and then we use machine learning surrogates again to calibrate them. So basically what we do is we build a calibration function with a machine learning model. And once you have that done that, what you can then do is predict actually what you actually wanted to do. So you want to say like, I actually wanted to have as many protons as possible, use my model calibrated with the experimental measurements and tell me where I have to look. And that's one of the workflows you can do with that. So that's one of the ways how you can build these up. So this is kind of like asynchronous streaming in experimental data, but it can go one step further. We had an example here on a short beamline that we have. What this one is trying to do is building a next generation light source. Usually they're like multiple kilometers long, like the one at SLAC is I think 1.5 miles long, and this one is only 10 meters. Not the same energy yet, but could be there on the same footprint. And what we try to infer is, going at the very end, what we can measure, what are the problems in the beamline, and what should we tune and detune to get a better result. So what we do is we really tightly connect also here measurements and experiments. And then what we can do, the simulations for these are that fast that we can actually, as we put in new data points in the simulation and the experiment, we can set up a simulation and let it actually just run as people click on it. I'm clicking on it. Does it play video? Nah, it doesn't play a video. All right, this is still. Oh no, it does move for you, right? Yeah, okay, good. Yeah. Okay, yeah. So you set something in experiment, we pick it automatically up from a control system and run simulations with them. And the simulations are sub-hertz in frequency for this case, because they are modeled with effective models and surrogates, so you can actually couple tightly. So that's fun. And that way you can actually inform as things are running. Now, the last point I want to make is, as we do build these surrogates and as we connect them with machine learning models, there's one technique that it's not new, but it had a really big renaissance in the last years that really enables a lot of fundamental AI/ML techniques. And that technique is called differentiable modeling. If we look at traditional simulations, what they do is they solve the so-called forward problem is by you give them a bunch of input parameters, let's say the 100,000 knobs you have in your accelerator, and they give you exactly one output, right? They give you the output for exactly this input. You can look at images, you can look at projections, whatever, but it's exactly this one state that you have simulated. The problem is, for all the examples I've shown you before, and for many more, what you actually would like to know is, given what I just saw, in which direction do I have to turn which knob now to get better? And these are essentially local gradients. So what differentiable modeling is doing is it does not only provide you this one point state output, but it shows you as many partial derivatives to as many inputs as you're interested in. So this is naturally great because if you know where to go next, you can write really great optimizers. But this is only the beginning of the story. The real cool thing is you can use this for combining HPC and AI/ML simulations. In particular, the following. Let's say you want to find out some really unknown properties somewhere in the middle of your simulation. What you can do is you can embed a neural network at a point where you want to know something, and you can, with these differentiable models, adjust the weights of this neural network until it matches what you observe at the end of your simulation. What you need for that is you need to be able to track all these gradients through your simulation, but once you have done this and with that adjusted the weights to your neural network, you have essentially a black box that you can then ask, hey, tell me what is the input to the unknown that I'm looking for. So it's essentially solving the problem that we have is like, I want to optimize for this unknown, what is the best initial input that I have to create here in a very effective way. And then way more things that you can do like this. But essentially, yeah, the whole thing is you want to track gradients for that. That is something that is currently absolutely not clear or not natural for HPC simulations. And it's things that you want to change at runtime. You want to at runtime say, by the way, I want for this input parameter the next output. And so I will show you in a second how this could be done, but this is really a thing where we're working on, and that helps a lot of science cases and is not natural for monolithic HPC. So what are the community chains we want to work on and exploring together? So I just talked about differentiable computing. There are right now that we see in our community a couple of prototypes where people just re-implement for fun HPC simulations that were written over decades in C++ and Fortran, in PyTorch, JAX, or Julia. And they make extremely good impact in science. So essentially they're eating our lunch, right? They fully ignore that you might need HPC. But what they show is that exactly the examples that I showed you, like reconstructing these inverse problems, can be done so effectively that it should not be ignored. At the same time, there's also a little bit of a tendency in HPC to be generally a little bit hostile against AI/ML, naturally because they take a lot of funds and a lot of air, but it doesn't help you, so we have to overcome that. What we're currently looking into is the following. To build differentiable software, I think what we need to do is we have to focus not on the lowest level, which are, for example, auto-differentiable models, to just recompile our whole codes. But I think we have to go to the algorithm level and build really modular pieces that are easy to differentiate. And then we have to glue them together on a scripting level. My preferred scripting level is Python, but it's only because the only one I know. I heard Julia is okay too. Just kidding, that's fine. But the point is really we have to write way more modular pieces, and then with that really extend our stacks. So the question for us is really, are we ready and eager to modernize our quite monolithic stacks where it's not only input file executable equals HPC workflow, but make them as modular and as fine that we can put these differentiable parts in there as we need them. And I think it fits very well. I mean, it is just an interoperability question. It is a software maintainability, it's a software observability and testability question to achieve this modularity. So I think this fits very nicely together once one sees the picture. Another thing I want to share and where I really need help is I showed you these vertical integrations, right? We're building dashboards where somewhere an HPC simulation is called. This takes the most resources, no question about this, but there's a lot of plumbing around this, going from servers to Kubernetes to blah, 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 building dashboards and showing them to our application end users. And so the question for us is a little bit like, how can we actually close the deployment gap here? The containers are a massive help there. We use containers on HPC systems to export things. And all we actually need to make this work is really to have like GPU-aware direct MPI host working. But this is actually pretty tricky, at least for the HPC systems we work with. They're like MPI file system performance issues everywhere. And it's not actually a problem that every HPC system uses their bespoke container software. But it's very hard for an application developer like us to maintain base images for every HPC system out there, build containers, tune them perfectly to the CPU and GPU microarch. And so naturally with packaging, but also with a lot of automation, we have to tune this and we have to really work on having base images for every site that is actually encouraged by the systems we're on. And last but not least, the last topic I want to show today and I want to discuss during this week with you. The other week in the CI working group, we started to look into questions like how could we make CI not only useful for correctness, but actually what we want to see is we want to have an observable and also actionable way to observe performance that we have. Because performance is the core thing of high performance software. And so the question is a little bit, how could we make this happen, right? We have the software in place, like we can record what we tested with CDash, but it changes a little bit. That's not actionable, right? We don't know if the runner was noisy. We don't know if, where we're currently on, and we have like a little bit of always a play between cost and observation. The same actually question comes through what Andrew mentioned before, through precision and quality. We have such a diverse set of contributors to our codes that it's not every one of those knows when they contribute a new quantum electrodynamics module that this might not run well on FP32, right? So let's make this as well observable on the PR basis. And so one thing that we recently found is there's a new cool service called CodeSpeed or CodeSpeed. I'm not sure that's how to pronounce it. What I do on a PR basis is you can expose them, for example, your PyTests underneath their C++, doesn't matter to them, and they can actually observe and measure them for you or actually emulate how they run, in some cases even on CPUs, without having this noise problem. And that's cool itself, but what's really interesting is you can zoom in and you can go, and, oh, by the way, because you changed this inner part of your C++ project, this is the part that gets faster and it gets slower. And that is extremely interesting and would work the same way actually to a certain extent to precision problems if we had the right tooling. So connecting what we already have with the proper feedback into CI would be extremely valuable for us. With that, I'll close out and we have still a few 3 minutes for questions with these summaries. Thank you for your attention.
Thank you. About CodeSpeed, so it's a tool that you've been playing with just recently. Do you feel like you have been using it long enough to be actually really confident about it, or you need to, maybe we'll meet in 6 months and you'll know better how relevant everything is?
That's a great question. I think the part that's relevant for us, and Alec looked this up quickly, is the interface that can present you the differences is open. That means we could tool it to whatever tool we want. The tool itself, I'm testing this for 2 months, it's okay. I think there are some bugs, but the interface is the one that I would like to target and put our own tooling there, HPC toolkit at all these things, yeah.
Just a tiny bit of a plug then for people. Tomorrow morning, we're having a CI/CD working group update talk, and I will talk about this a little bit more because, yes, Axel, I want to help support you and get you to a place that you can do performance testing in CI.
We have 5 more minutes, so don't hold back with really complicated questions.
So I have 2 questions. You can take one or both. So one is on the top of your wish list for if you could ask for and get one thing from hardware or networking, whatever, for your workflow, what would make the biggest difference? And second is when you talk about, so the second one is you talk about not just executable plus inputs, but finer granularity. Are you thinking at the level of a time step in each process call, or what level of granularity? So 2 questions.
Okay. The second one, you mean the differentiable? Okay, differentiable granularity. I'm thinking about the granularity essentially like a Poisson solver, a getter-scatter operation on a physical field. That, or like an ImpactX would be a symplectic map update, an integrator. So more than an individual operation as we usually expose them, but also less than a whole time step. Make a wish, good question. In hardware or interfacing, or interconnect. I mean, for pure for a long time, our biggest bottleneck was the GPUs have too small memory. I think that just got better, like last year. The bottleneck that we face right now, and that's imminent end of this year, is that we are not ready for FP32. We try to. We have a proposal in the pipeline that's hopefully funded, but it's urgent. I think though that's the right push though, because for a long time HPC we just ignored that we could get a factor 2x speed up for FP32, but it will be tricky. There's definitely there would be a near impossible for a lot of algorithms that we have to go to FP16. There are a few points where we know where it helps, but it's then you counterplay it with more compute, and at some point you don't get the speed up anymore. So my wish would be that keep it chill with FP32, please, at least. Otherwise, networking, a lot of the algorithms, if you go at really large scale and you have really large load balances, networking is a challenging part always. Anything that we can do to hide more latencies. I always think admittedly more from a software perspective. I think we have a lot to do to do less bursty MPI communications generally in HPC, try to drag them out more. But anything that helps to not pile up too much communications and hardware I think is extremely valuable at scale. Yeah. More pain points about my container usage. But I can elaborate there a little bit. My honest question though, right? Containers are great, but they have to be small enough to be run, right? So I cannot just build one Docker container for the world of WarpX. I need one that's perfectly tuned for the Ampere GPUs we have in Perlmutter. I need one that's perfectly tuned for the AMD GPUs that are running on Frontier or Tuolumne. You need the same for the CPU micro arches. And you need always come from a certain base stack, right? So as a maintainer, the challenge, what I'm shouting out here is a little bit is, we're already supporting 4+ package managers, obviously having one preference. But when you have the same thing then for all the automations for Docker containers, they could use those package managers. We have to really consolidate as much as possible our deployment there. And it starts really with good base images for the centers we run on. I'll take it. Yep, I'll take it.
You talked about differentiable programming. You can use, like, for example, Cocos, and there's a Staccato package in Trilinos that has 80 types. Have you thought about trying this within the C++ approach?
Oh. Yeah, that's a good point. For a lot of the algorithms that we use in accelerator modeling, they don't immediately apply. There are differentiable models there, but they're usually forward differentiable only, and the backwards differentiable part is the one that's really interesting for us. Yeah, both needed. Yeah, but I thought initially for the last year that I just want to do a monolithic auto differentiation of our codes with Enzyme on the LLVM level or with CLAD, but it's not scalable, and it also contradicts the user experience and wish that you want to actually at runtime kind of configure, I need for this input the gradients as well, and then you would run an HPC simulation through a compiler, sometimes in a single translation unit. It's not scalable. So due to that, I think it's a combination of both. where you have good algorithms that work straightforward, that helps a lot. And specifically, if you can accelerate and save memory on backwards differentiability, their algorithmic innovation is desperately needed. Yeah.